Hello students, in today's lecture we will study about valence shell electron pair repulsion VSEPR theory, valence bond theory and hybridization. This is given in class 11 chemistry of NCERT syllabus, which is rationalized for the year 2023-24, and this is our lecture number 3 of unit 4. In this section we will study about valence shell electron pair repulsion VSEPR theory, valence bond theory, orbital overlap concept, directional properties of bonds, overlapping of atomic orbitals, types of overlapping and nature of covalent bonds, the strength of sigma and pi bonds, and in the end we have also included a section on hybridization. We will answer some multiple choice questions also. This is a very important and elaborate chapter. Please listen to my lecture very carefully, word by word, and note down all the important points. I welcome you once again. Before we study about VSEPR theory, let us recapitulate what we have studied about chemical bonding. Chemical bond. We have studied that the force of attraction which holds chemical entities in different species is called a chemical bond. So chemical bond is the force of attraction which holds various chemical entities in different species. Whereas electrovalent bond is the attractive force between the oppositely charged ions which comes into existence by transference of electrons. Electrovalency valency is the number of electrons which an atom loses or gains while forming ionic or electrovalent bonds. Covalent bond. Covalent bond comes into existence by mutual sharing of electrons by atoms participating in the process of bonding. Valence bond approach of covalent bond. The bond is formed by overlapping of half-filled atomic orbitals having electrons with opposite spins. Covalency is the number of half-filled atomic orbitals which an atom provides for participation in overlapping at the time of bonding. Coordinate bond or dative bond. The bond is formed by sharing electrons in which the shared pair of electrons is contributed by one of the atom called donor while the other atom is called acceptor. Electronegativity. Electronegativity is the power of an atom to attract bonding pair of electrons towards itself. Dipole moment. Dipole moment is a vector quantity defined by the product of charge developed on any atom and the distance between the atoms, creating a dipole, and its symbol is mu. Polar and nonpolar molecules. The molecules with dipole moment mu greater than 0 are called polar molecules, while those with mu equal to 0 are nonpolar molecules. Dipole-dipole interactions. The attractive interactions among the opposite ends of polar molecules in liquid and solid state is called dipole-dipole interaction. Finally, we have also studied in our previous video about resonance. When a molecule is represented by more than one electronic arrangement, none of which is able to explain the observed characteristics of the molecule, then the actual structure is intermediate of various electronic arrangements and it is known as resonance hybrid. The various electronic arrangements are called resonating structures or canonical structure. Now we will proceed with the contents of this video. And the first, Lewis concept is unable to explain the shapes of molecules. This theory provides simple procedure to predict the shapes of covalent molecules. Sidgwick and Powell in the year 1940 proposed a simple theory based on the repulsive attractions of the electron pairs in the valence shell of the atom. It was further developed and redefined by Nyholm and Gillespie in the year 1957. The main postulates of VSEPR theory are as follows. The shape of molecule depends upon the number of valence shell electron pairs. Please note, the shape of molecule depends on the number of valence shell electron pairs, which may be either bonded or non-bonded around a central atom. Pairs of electrons in the valence shell repel one another since their electron clouds are negatively charged. These pairs of electrons tend to occupy such position in space that minimize repulsion and maximize the distance. So, the realignment of electrons results in minimizing repulsion and this is to maximize the distance between them. There may be an objective type questions on these statements. The valence shell is taken as a sphere with the electron pairs localizing on the spherical structure at a maximum distance from one another. A multiple bond is treated as if it is a single electron pair and two or three electron pairs of multiple bond are treated as single super pair. Where two or more resonance structures can represent a molecule, the VSEPR model is applicable to any such structure. The repulsive interaction of electron pair decreases in the order such that lone pair to lone pair, the repulsive reaction, the lone pair to lone pair reaction interaction is greater than lone pair to bond pair interaction, which is greater than bond pair to bond pair interaction. Please note there will be an objective type questions on this statement, that is the repulsive interaction of electron pair decreases in the order lone pair is greater than lone pair bond pair and bond pair which is greater than bond pair bond pair. Nyholm and Gillespie in the year 1957 refined the VSEPR model by explaining the important difference between lone pairs and bonding pairs of electrons. The lone pairs are localized on the central atom. Please see the figure here shown on the screen. In the screen, nitrogen is the central atom, H and H are surrounding atoms. As a result of the lone pair electrons in a molecule which occupy more space as compared to the bonding pairs of electrons. This results in greater repulsion between lone pairs of electrons as compared to the lone pair bond pair and bond pair bond pair repulsions. These repulsions affect the result in deviation from the idealized shapes and alterations in the bond angles. Hence, due to the repulsion effects, the shapes get altered in bond angles and in molecules. For the prediction of geometrical shapes of molecules with the help of VSEPR theory, it is convenient to divide molecules into two categories. One as the molecules in which the central atom has no lone pair. As shown in the figure here, BE is the central atom and Cl is the Cl2Cl are the surrounding atoms. The second category will be for discussions molecules in which central atom has one or more lone pair. For example, in the figure 3 here, boron B is the central atom, F and F are the surrounding atoms, and this is a planar trigonal shape. Examples of shapes of molecules in which central atom has no pairs are BeCl2, which is shown on the screen, where the electronic configuration is 1s1, 2s2, and for Cl it is 2. And another example is Bf3 shown on the screen, where the electronic configuration is 1s1, 2s2, 2p1, and there are 3 fluorine atoms. Some more examples of molecules in which central atom has no lone pair are BeCl2, which is linear molecule and the angle is 180 degrees. Bf3 with 3 bonds and the angle between 2 bonds is 120 degrees. CH4 and PCl5 are some other examples. Table 1 shows the molecules in which the central atom has no lone pair. The molecule types may be AX2, AX3, AX4, AX5 and AX6, which are shown in column number 1 of the table 1. The column number 2 shows in respect of AX2 the number of electron pairs are 2 and the predicted geometry is linear and it is shown representative structure is shown. Here there are 2 bonds. Number of electron pairs are 2, here 1 and here 2, and X is the central atom. So the angle between them is 180 degrees. Example of such cases are HgCl2 or BeCl. The next molecule type is AX3, where number of electron pairs are 3 and the predicted geometry is trigonal. See, this is the trigonal and central atom is here and there are 3 surrounding atoms. Examples are BF3, BCl3. The next molecule type is AX4, where number of electron pairs are 4 and the shape predicted geometry is tetrahedral. And this representative structure is shown in the table. And examples of such tetrahedral geometry are CCl4, CH4 and SiCl4. In the case of AX5 type of molecule, there are 5 electron pairs and the predicted geometry is trigonal bipyramidal. So it is trigonal. In the explain it is trigonal and it is in the top there are 2 pyramids. See, please see in the figure, these are lone pairs. The 2 dots are lone pairs and all other straight lines are bonds. So this is This is a lone pair, this is a lone pair, this is lone pair. There are four lone pairs. Examples of such molecules are PCl5 and PF5. The last and final molecule type is AX6, where the number of electron pairs are 6 and the shape is octahedral, and the shape is shown in the table. Examples of such octahedral molecules are SF6 and PF6 minus. After studying the no lone pair cases of molecules, we will take up molecules in which central atom has one or more pairs. So CH4, first is CH4, where number of pairs are 4 and number of lone pairs are 0. Here you see the number of lone pairs are 0, but structure is tetrahedral. And the molecular shape is shown in the figure, which is tetrahedral, and the bond angle in degrees is 109.5 degrees. The next case is NH3, where number of bond pairs are 3 and number of lone pairs are 1, and its shape is molecular geometry is trigonal pyramidal, trigonal pyramidal. So shape is shown here with H atom, 3 H atoms, and number of lone pairs are here is shown with the dot. And the bond angle in this case is 107.3. Another example is H2O, where number of bond pairs are 2 and number of lone pairs are 2, angular or bent. The molecular shape is angular or bent. The molecular shape is shown on the screen, and the bond angle is 104.5. Valence band theory. Lewis' approach helps us in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecules. Valence bond theory was introduced by Hitler in the year and London in the year 1927 and developed further by Pauling and others. When two hydrogen atoms A and B approaching each other having a nuclei Na and Nb respectively, and electrons present in them are represented by small Ea and Eb, E subscript B, and when these atoms are at a large distance from each other, there is no interaction between them. So please see the figure here. When there is a large distance between the two atoms, there is no interaction. As these two atoms approach each other, new attractive and repulsive forces begin to form. So as they are approaching nearer, new attractive and repulsive forces begin to operate. Attractive forces arise between nucleus of one atom and its own electron, that is Na minus Ea and Nb minus Eb. Nucleus of one atom and electron of other atom, that is Na minus Eb and Nb minus Ea. Similarly, the repulsive forces arise between electrons of two atoms and nuclei of two atoms. Attractive forces tend to bring the two atoms close to each other, whereas the repulsive forces tend to push them apart. Experimentally, it has been found that the Magnitude of new attractive force is more than the new repulsive forces. As a result, two atoms approach each other and potential energy decreases. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and the system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having the bond length of about 0.74 Armstrong. This is shown in the figure. So this stage is due to two hydrogen atoms which are bonded together to form a stable molecule. This is a stable molecule status having bond length of 0.74 Armstrong. Since the energy gets released when the bond is formed between the two hydrogen atoms, the hydrogen molecule is more stable. Here, the hydrogen molecule is more stable than that of the isolated hydrogen atoms. The energy so released is called bond enthalpy, which is corresponding to a minimum in the curve shown in the figure. This is about 400 so to the minimum energy is about 436 kilojoules of energy is required to dissociate 1 mole of the hydrogen molecule. Bond is formed due to interaction of valence electrons. The core electrons do not participate in the bond formation. During bond formation, only valence electrons lose their identity. Bond formation is accompanied by release of energy and this accounts for stability of atoms. Stability of the bond. The mole has minimum energy at equilibrium distance known as intermolecular distance. This is intermolecular distance. Larger the decrease in energy, stronger will be the bond formation. So to recapitulate, I will explain this figure once again. The potential energy curve for the formation of hydrogen molecule as a function of intermolecular distance. This is the intermolecular distance is shown on the figure. The minimum in the curve, this is the minimum in the curve, corresponds to the most stable state of hydrogen. This is molecules are farther apart, hence there is no force of attraction or repulsion. As they come closer, the forces of interaction of valence electron starts. So bond is formed here. Types of overlapping and nature of covalent bond. When two atoms approach each other, overlapping of atomic orbital takes place to give molecular orbits. When orbitals of two atoms come close to form bond, their overlap may be positive, negative or zero depending upon the sign, that is phase and direction of orientation of the amplitude of the wave function. Please note that the overlap may be positive, negative or zero depending upon the sign and the direction of orientation of the amplitude of the wave function in space. Sigma bond is formed by head-on overlap of the atomic orbital along with internuclear axis, and this type of combination is shown by SS, SP and PP overlapping. So in case of sigma bond, there may be SSO or S-P and P-P overlapping, and this is shown in the figure. In the figure, the first diagram shows s orbital and s orbital come closer and combine to form an S overlapping. Please see the central part is overlapping, and this is called SS overlapping. Then in the case of sp overlapping, please see here there is an s orbital and p orbital. If we have to recall the shapes of orbitals, s orbitals and p orbitals. So p orbital is in the form of a dumbbell and this is a sphere. So they combine to form, and the overlap is as shown in the figure, and this is called S-P overlapping. The third case is P-P overlapping. This P-P overlapping is also shown on your screen with two dumbbells. This is one p orbital and this is second orbital. Both of them combine, that is p orbital plus p orbital overlap to form P-P overlapping, and the darkened part is the overlapping area. There can be a pi bond. There is another form of bond called pi bond, which is formed by lateral overlapping. See here, there was previously it was horizontal, now it is lateral, that is vertical. So this is a vertical plus 10. They combine this p orbital and this p orbital combine to form the overlaps, two overlaps as shown in the figure. Such an overlapping is exhibited by only by p orbital. Please note, pi bond is formed by only p orbital. Strength of sigma and pi bonds. Basically, the strength of bond depends on the extent of overlapping. In the case of sigma bond, the overlapping of orbital takes place to a large extent. Hence, it is stronger as compared to the pi bond, where the extent of overlapping occurs to a smaller extent. Please see the figure here. The overlapping area is small. So, whereas in the case of SS orbital, the overlapping orbital takes place to a large extent. So, large extent the overlap is taking. So, S orbitals are stronger as compared to the p bond. So, S bonds are stronger than the p bonds. Further, it is important to note that formation of multiple bonds between two molecules of atom, pi bond is formed in addition to sigma bond. In such cases, there is increasing order of bond energy. So, the weakest is the single bond. Single bond is weaker than double bond, which is weaker than triple bond. Hence, triple bond is the strongest in the bond energy. Then, for bond length, single bond is larger than double bond, and which is triple bond. So, triple bond is the smallest. So, double bond is greater than triple bond and single bond is the longest, increasing the order of reactivity. So, in case of reactivity, single bond is weaker, is less than double bond, which is less than triple bond. So, reactivity is more in triple bond. Hybridization. In order to explain the characteristic geometrical shapes of polyatomic molecules like CH4, NH3 and H2O etc., Pauling introduced the concept of hybridization. So hybridization is the process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energies and shape. For example, when 1, 2s and 3p orbitals of carbon hybridize, there is formation of 4 new sp3 hybrid orbitals. Please consider the example of beryllium atom shown on your screen. In the ground state, beryllium atom has 1s, 2s and 3p orbitals. When it is excited, that is, in the excited state, beryllium atom will have 1s, 2s and 2p orbitals as shown in the diagram. So, you please see the redistribution of electrons in 2s and 2p orbitals. Salient features of hybridization. The number of hybrid orbitals is equal to the number of atomic orbitals. Please see here, there is no change in the number of orbitals. That is, in the hybrid orbitals, the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. The hybridized orbitals are always equivalent in energy and shape. The hybrid orbitals are more effective in forming stable bonds. Please underline in forming stable bonds than pure atomic orbitals. That is, in the ground state, they are not as stable as in hybrid state. The hybrid orbitals are directed in space in some preferred direction to have minimum repulsion. So the objective of hybrid orbitals is to have minimum repulsion between electron pairs and thus a stable arrangement. Therefore, the type of hybridization indicates the geometry of molecules. Important conditions for hybridization. The orbitals present in the valence shell of atom are hybridized. Please see that the valence shells are 2s and 2p. So the orbitals present in the valence shell of the atom are only hybridized. The orbitals undergoing hybridization should have almost equal energy. Promotion of electron is not an essential condition prior to hybridization. It is not necessary that only half-filled orbitals participate in hybridization. In some cases, even the filled orbitals of valence shell take part in hybridization. Types of hybridization. There are 3 types of hybridization depending on the types of orbitals involved in mixing, such as sp3, sp2, sp, sp3d, sp3d2, etc. First, let us consider the example of sp hybridization. In this hybridization, 1s and 1p orbitals hybridize to produce two equivalent hybrid orbitals known as sp hybrid orbitals. The two sp hybrid orbitals are oriented in a straight line, making an angle of 180 degrees, and therefore the molecule possesses linear geometry. Each of the hybrid orbitals has 50% s character and 50% p character. Examples of molecules having sp hybridization are BeF2, BeCl2, BeH2, etc. Let us consider example of BeCl2. The ground state of electronic configuration of Be is 1s2, 2s2. This ground state is not shown in your figure on the screen. The figure on the screen shows the excited state of one of the 2s electrons, which is promoted to the 2p orbital to account for its valency. So, in the excited state, one of the orbital electrons is promoted to 2p orbital to account for its bivalency. One 2s and one 2p orbitals get hybridized to form two sp hybridized orbitals. So this is hybridized orbital. So two sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degrees. Each of these sp hybridized orbital overlaps with the 2p orbitals of chlorine axially and form two BeCl sigma bonds. The figure on the screen shows the formation of sp hybrids from s and p orbitals. So figure A shows the formation of s and p orbitals. So this is an s orbital and this is a p orbital. The figure B shows the formation of linear BeCl2 molecules. See here, this is ClPz, this is the chlorine atom, and this is also in the Z orientation, two chlorine atoms, and the central one is Be, which is shown here. sp2 hybridization. In this hybridization, one s and one 2p orbitals hybridize to produce three equivalent hybrid orbitals known as sp2 hybrid orbitals. sp2 hybrid orbitals are larger in size than sp hybrid orbitals, but slightly smaller than that of sp3 hybrid orbitals. Each sp2 hybrid orbital has one third, that is 33.33% s characters, two-thirds or 66.7% p characters. Examples of sp2 hybridization are bf3, bcl3, bh3, etc. Let us consider the example of bcl3. The figure shows the ground state electronic configuration of central boron atom, which is 1s2, 2s2 and 2p1. So this is the ground state, and this gets excited and becomes one of the 2s electrons is promoted to vacant 2p orbital, here shown here in the excited state, 2p orbitals. As a result of boron has three unpaired electrons, that is one 2s, one 2s and 2p and two numbers of 2p, which hybridize to form sp2 orbitals, and these three hybrid orbitals so formed are oriented in triagonal planar arrangement and overlap with the 2p orbitals of chlorine to form 3 B-Cl bonds. Therefore, in BCl2 shown in the figure, the geometry is triagonal planar with C1 BC1 bond angle of 120 degrees. So here you see here the angle between C1 BC1 bond angle is 120 degrees. sp3 hybridization. In this hybridization, 1s and 3p orbitals intermix to form sp3 hybrid orbitals of equivalent energy and identical shape. These four sp3 hybrid orbitals are directed towards the four corners of a tetrahedron separated by an angle of 109 degrees 28 seconds or approximately 109.5 degrees. sp3 hybrid orbitals have 1/4, that is 25% s characters, and 3/4 or 75% p character. Examples of sp3 hybridization are CH4 and NH3. Please see the figure shown on the screen. Here, the carbon atom in the ground state as well as excited state is shown above in the upper part of the figure. So, this is the ground state and this is the excited state. So, for hybridization, when it gets excited, the carbon 2p and 2s combine to form the 4 sp3 hybridization or sp3 orbitals as shown in the figure. The figure below shows the formation of sp3 hybrids by combination of s, pz, px, py and pz atomic orbitals of carbon and the formation of CH4 molecule. Other examples of sp3 hybridization are NH3 and H2O. sp3 dehybridization. This type of hybridization involves mixing of 1s, 3p and 1d orbitals to form 5 sp3 dehybridized orbitals which adopt trigonal bipyramidal. Formation of PCl5. The ground state electronic configuration of phosphorus is 1s2, 2s2, 2p6, 3s2 and 3p3. Under the conditions of bond formation, the 3s electrons get unpaired and one of the electron is promoted to the vacant 3dz2 orbital. The ground state and excited state configurations of phosphorus are shown on the screen. So this is the P phosphorus ground state. And the ground state there are 3p and 4 3d orbitals. In the excited state one of the electrons gets promoted and moves to 3d. When these combine all together, 3s, 3p and 3d, sp3d orbitals filled by electron pairs donated by 5 Cl atoms are shown. Here, the Cl5 atoms are shown here. PCl5 atoms and configuration geometrical is which is shown on the screen is that of PCl5. sp3d2 hybridization. In this type of hybridization, 1s, 3p and 2d orbitals undergo intermixing to form 6 identical sp3d2 hybrid orbitals. These 6 orbitals are directed towards the corner of a octahedron and lie in the space at an angle of 90 degrees to one another. For example, formation of SF6. The ground state outer configuration of 16s, that is the valency of sulfur is 16, is 3s2 and 3p4. In the excited state, the electron pairs in 3s and 3px orbitals get unpaired and one out of each pair is promoted to vacant 3dz2 and 3dx2 and dy2 orbitals. The ground state and excited state configuration of 16s are shown on the screen. So this is the ground state of S sulfur. So there are 3s, 3p and 3d orbitals. In the excited state, electrons are redistributed in 3s, 3p and 3d as shown on the screen. This is the excited state and this is the ground state. So SF configuration, there are 6 fluorine orbitals which combine to form sp3d2 hybridization, and its geometry is shown on the figure. And the shape of this geometry is octahedron. So some more examples of hybridization and structures of molecules having bond pairs only. That means lone pairs are absent in this. Examples are here: sp, sp2, sp3, dsp2, dsp3 or sp3d or d2 sp3 or sp3d2 and d3 sp3 or sp3d3. The corresponding number of orbitals are for sp it is 2, for sp2 the hybrid orbitals are 3, for sp3 hybrid orbitals are 4. For even for dsp2 the number of hybrid orbitals are 4. For dsp3 or sp3d the number of hybrid orbitals are 5. In the case of D2sp3 or sp3d2, the number of hybrid orbitals are 6. For D3sp3 or sp3d3, the number of hybrid orbitals are 7, and the shape of sp is linear and bond angle is 180 degrees. Other examples of sp hybridization in the absence of lone pair are BeCl2, BeF2, etc., which are written on the extreme right hand side of your screen. Please pause this video and note down all the figures. For sp2, where the number of hybrid orbitals are 3, The shape of molecules is triangular planar and bond angle is 120 degrees. Example are BF2, BCl3, etc. etc. For sp3, where the number of hybrid orbitals are 4, the shape of molecules is tetrahedral and its bond angle is 109 degrees 28 seconds. And examples are CH4, CCl4, etc. For DsP2, the number of hybrid orbitals are 4 and the shape is square planar, angle is 90 degrees. Example is PCl4 with 2 negative electrons. Other examples for DsP3 and others are shown on the screen. Please pause this video and note down all the details. Next, we will consider the examples of hybridization and structures of molecules having lone pairs. Lone pair may be 1, 2 or etc. as well as bond pairs. The details are given on the screen. Please pause this video and note down all the details. For example, if the type of molecule is AX2, the number of bonds are 2 and number of lone pairs are 1. And hybridization type is sp2, where the bond angle is 120 less than 120 degrees and the expected geometry is trigonal planar and actual geometry is V-shape or bent. Examples are SO2, SnCl2, PbCl2, O3. The next case is if the type of molecule is AX2, where the number of bond pairs may be 2, number of lone pairs are 2, and hybridization type is sp3 and bond angle is 109 degrees 28 seconds. The expected geometry is tetrahedron and the actual geometry is V shape or bent shape. Examples are H2O, H2S, etc. So please pause the video and note down all the contents of this table as examples of molecules having lone pairs as well as bond pairs. Now we will answer some of the MCQs. Question number 1. According to VSEPR theory, 4 options are given. You have to identify the correct answer. Option A, the shape of the molecule depends upon the bonded electron pairs. Option B, pair of electrons attract each other in valence shell. Option C is the pairs of electrons tend to occupy such positions that minimize the repulsions. And option D is the pairs of electrons tend to occupy such positions that minimize distances from each other. You have to examine, pause the video and mark your answer. I will give the explanation. So the correct answer is, according to VSEPR theory, the pairs of electrons tend to occupy such position that minimize repulsions. Next question. In a bonded molecule, the order of repulsion between bonded and non-bonded electron is option A, LP-LP greater than BP-BP greater than LP-BP. Option B, B pair greater than LP pair greater than LP-BP. Option C, lone pair greater than lone pair greater than bond pair. Option D is bond pair greater than lone pair and lone pair dash lone pair. So you have to identify and mark the correct order of repulsion between bonded and non-bonded pairs. So examine and mark the correct answer. I will give the correct answer is lone pair greater than lone pair greater than bond pair order of repulsion. Next question. The shape of water molecule which should be tetrahedron has a bent or distorted tetrahedral shape with a bonded angle of 104.5 degrees. What could be the reasons for this? That is, you have to mark the reason for which mark the reason for bending angle, getting the reduced. So the reason may be LP-LP repulsion is greater than LP-BP repulsion. LP-BP repulsion is greater than LP-LP repulsion. Option C is LP-LP equals LP-BP repulsion, and option D is presence of lone pair does not affect the bond angle. Please examine, pause the video and mark your answer. The bonded angle in this case is reduced to 104.5 degrees from 109.5 degrees. This is due to LP-LP repulsion, which is greater than LP-BP repulsion. Next question. In which of the following molecules the central atom does not retain any lone pair of electron? So you have to identify the molecule in which the central atom does not retain any lone pair of electron. Option A NH3, option B NO3, option C BF3, and option D is H2O. So you have to identify the correct answer and mark it. Please pause and mark your answer. The correct answer is in all other molecules, N and O retain lone pair of electrons. Hence, the correct answer is BF3. So, in BF3, the central atom does not retain any lone pair of electron. Please mark it. Next question. The molecule like BRF5 and XeO4 are square pyramidal in shape. What is the type of hybridization shown in this molecule? So, four options are given. Option A DsP3, option B DsP2, and option C sp3d, and option D sp3d2. You have to pause the video and mark your answer. I will give the correct explanation. BRF5 and XeOF4 have sp3d2 hybridization. Hence, their shape is square pyramidal. So, the shape of BRF5 and XeO4 have sp3d2 hybridization. This option is given as option D, and you please mark it. Next question. Which of the following shows DsP2 hybridization and a square planar geometry? Four options are given. Option A SF6, option B BRF5, option C PCl5, and option D NiCN4 with two negative electrons. The correct answer is option D. Please mark it. You have to remember and mark the correct answer. Next question. Which of the following pairs are isostructural? Four options are given. SO4 2 minus and BF4 2 minus. Option B NH3 and NH4 plus. Option C CO3 2 minus and CO2. And option D CH4 and BF3. SO4 2 minus and BF4 minus have sp3 hybridization and are tetrahedral in shape. So correct answer is option A. Next question. CF4, SF4 and Xe4 contain the following electronic structures on their central atom. Which one is the correct option? Option A, 1, 2 and 3 lone pairs of electrons respectively. Option B, 0, 1 and 2 lone pairs of electrons respectively. Option C, 1, 1 and 2 lone pairs of electrons respectively. Option D, no lone pairs of electrons on any molecule. Please examine the options, remember, recall of memory, and note that CF4 is sp3 tetrahedral but no unpaired electron. So here the item is 0. The first should be 0. So option B is the correct answer. The other explanations are also given. Pause the video and note down. The option is B. Next question. Which of the following statement is not true? Option A. Ionic bonds are non-directional while covalent bonds are directional. Option B. Formation of pi bond shortens the distance between two cornered atoms. Option C. Ionic bond is possible between similar and dissimilar atoms. Option D. Linear overlapping of atomic p orbitals leads to sigma bond. You have to remember and mark the correct answer. The correct answer, that is the wrong statement, is ionic bond is possible between similar and dissimilar atoms. So this is not possible. So this answer is wrong answer. Wrong option. Next question. Which of the following orbitals will not form sigma bond after overlapping? S orbital and S orbital, S orbital and pz orbital, pz orbital and pz orbital, px orbital and px orbital. So the correct answer is, you have to remember and mark the correct answer. Px orbital and px orbital will not form sigma bond after overlapping. Next question. Which type of overlapping is shown by P, that is px, py and pz orbitals? Option A, 2 end-to-end and 1 sidewise overlap. Option B, 2 sidewise and 1 end-to-end overlap. Option 3, 3 sidewise overlaps. Option D, 3 end-to-end overlaps. Pz orbital by convention undergoes end-to-end overlapping and px, py undergo sidewise. So the correct answer is option B. So there are 2 sidewise overlapping and 1 end-to-end overlap. The last question. How many sigma and pi bonds are present in toluene? Option A, 10 sigma and 3 pi bonds. Option B, 12 sigma and 3 pi bonds. Option C, 15 sigma and 3 pi bonds. Option D, 6 sigma and 3 pi bonds. So pause the video and mark your answer. So the structural diagram of toluene, that is C6H5CH3, is shown on the figure, which has number of sigma bonds, where sigma bond are 15 and pi bond is 3. So the option C is the correct answer. Please mark it. With this, we come to the end of lecture number 3. In the next lecture, that is lecture number 4, we will discuss about molecular orbital theory, bonding in some homonuclear diatomic molecules, and hydrogen bonding. Till then, goodbye.